examples on primes and congruence relation. The first example, find remainder of 8 raised to 402 is when divided by 13. Now, to determine the remainder of this number, we are going to use the Fermat theorem. As we know that if P is a prime and P does not divide A, then A raised to P minus 1 congruent to 1 modulo P. Now here A is equal to 8 and P is equal to 13, and 13 does not divide 8, so from this we can write 8 raised to 13 minus 1 congruent to 1 modulo 13, that is 8 raised to 12 congruent to 1 modulo 13. So this is equation number 1. Now we reach up to 8 raised to 12 and we want to determine 8 raised to 402. So again, by using division algorithm, if we divide 402 by 12, then the quotient will be 33 and remainder is equal to what? 6. So here 8 raised to 402 is equal to 8 raised to 12 raised to 33 in plus 8 raised to into 8 raised to 6. So as we know that 8 raised to 12 congruent to 1 modulo 13, and therefore 8 raised to 12 raised to 33 congruent to 1 raised to 33 mod 13, that is 8 raised to this 33 into 12 is equal to 396. 8 raised to 396 congruent to 1 modulo 13. So this is equation number 2. So now we arrive up to 396 and we want to reach up to 402. So that is, we need more 8 raised to 6 power. So as we know that 8 raised to 2, that is 64, which is congruent to 8 raised to 2 64, which is congruent to 12 modulo 13, and therefore 8 raised to 2 that is 12 raised to 2, which is equal to 104, which is congruent to 1 modulo 13. If we divide 144 by 13, then it is equal to 1 modulo 13, that is 8 raised to 4 congruent to 1 modulo 13. So if you multiply these two equations, then we get 8 raised to 6 congruent to 12 modulo 13. If you multiply these two equations, if you 8 raised to 2 into 8 raised to 4, it is 8 raised to 6, 12 into 1 is what? 12 modulo 13. Say this equation number 3. So from equation number 2 and 3 we can write, what is equation number 2? It is what? 8 raised to 396 congruent to 1 modulo 30. From this 8 raised to 396 and 8 raised to 6 congruent to 12 into 1 modulo 13. So total 8 raised to 402 congruent to 12 modulo 13, and therefore when we divide the given number by 12, the remainder is equal to what? When we divide 804 raised to 2 by 13, the remainder will be what? remainder is 12. Example number 2. Example number 2. Find all pairs. Find all pairs I bar and J bar in Z10 such that I bar into J bar is equal to 1. J bar equal to 1. Again, for I bar in Zn, there exists J bar in Zn such that I bar into J bar is equal to 1 if the GCD of I and N is equal to 1. So here given Z10, which is equal to 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, 7 bar, 8 bar and 9 bar. So again here the GCD of 1 and 10 is 1, the first pair. Again GCD of 2 and 10 is greater than 2. Next GCD of 3 and 10 is equal to 1. GCD of 10 and 4 is 2, so it is again not there, does not exist J such that. Next GCD of 5 and 10 is 5. Then 6 and 10 is 2. Again there exists a pair 7 and 10, their GCD is 1. And there is one more 9 and 10, their GCD is 1. So there exists a number 1. So what is here pair? First 1 bar into 1 bar is equal to 1. Then next number 2 1 bar. Next we want to determine 3. So as we know that 3 bar into 7 bar is equal to 21 bar, and which is equal to 1 bar. So the 3 bar into 7 bar is 1. Again 7 bar into 3 bar is equal to 1 bar. And number 4, 9 bar into 9 bar, which is 81, and 81 congruent to what? 1 bar modulo 10. So there exist only 4 pairs such that I bar into J bar is equal to what? 1. So this is the answer. I bar into J bar is what? 1 in Z10. Example number 3. Which elements satisfy the equation? Which elements in Z6 satisfy the equation x square is equal to x? Satisfy the equation x square is equal to x. Now if we list all the elements of Z6, we get here Z6 is equal to 0 bar, 1 bar, 2 bar, 3 bar, 4 bar and 5 bar. Now 0 bar square is equal to 0 bar, 1 bar square is equal to 1 bar, 2 bar square is equal to 4 bar, 3 bar square is equal to 9 bar, and 9 bar congruent to what again? 3 bar modulo 6. Then 4 bar square is equal to 16 bar, and 16 congruent to what again? 4 bar modulo 6. And next 5 bar square is equal to 25, and 25 congruent to what? 1 bar modulo 6. So the answer is what? The solution is what? 0 bar, 1 bar, 2 bar, 3 bar and 4 bar. As 0 bar square is 0 bar, 1 bar square is 1 bar, 2 bar square is equal, not 2 bar, sorry, this is 2 bar is not answer here, sorry, 0 bar you can check here, this is one first answer, 0 bar square, then 1 bar square is 1 bar, 3 bar square is 3 bar, and 4 bar square is what, 4 bar. Again next, list similarly, find all the elements in Z8 such that having x square is equal to x. If we list all the elements of Z8, we get Z8 is equal to 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, 7 bar, okay, and 0 bar square is equal to 0 bar, 1 bar square is equal to 1 bar, 2 bar square is equal to 4 bar, 3 bar square is equal to 9 bar, which is again 1 bar, 4 bar square is equal to 16 bar, which is equal to 0 bar. Then next 5 bar square is equal to 25, 25 is equal to 1 bar, 6 bar square is equal to 36, and 36 congruent to what, 4 bar modulo 8. Then next 7 bar square is equal to 49, and 49 congruent to what, 1 bar. So here there exists only two solution here, that is 0 bar and 1 bar, such that their square is again itself. So this is the only solution. Next example, example number 4. Write our addition and multiplication table for addition and multiplication table for Z4. First addition table, want to insert table here, 0 bar, 1 bar, 2 bar, 3 bar, 0 bar, 2 bar, 3 bar. So here 0 bar, 1 bar, 2 bar, 3 bar under addition. Here 0 bar, 1 bar, 2 bar, 3 bar. Then 0 bar plus 0 bar is 0 bar. Then 0 bar plus 1 bar is 1 bar. 0 bar plus 2 bar is 2 bar. And this is what, 3 bar. 1 bar plus 0 bar, 1 bar, 2 bar, 2 bar plus 1 bar, 3 bar, and 1 bar plus 3 bar is 4 bar, which is equal to again what, 0 bar. 2 bar plus 0 bar, 2 bar. Then here 3 bar, 2 bar plus 2 bar, 4 bar, which is equal to what, 0 bar. And 2 bar plus 3 bar is equal to say 5 bar, which is equal to what, 1 bar. Next 3 bar plus 0 bar is 3 bar. 3 bar plus 1 bar, 4 bar, 0 bar. 3 bar plus 2 bar, 5 bar, which is 1 bar. And 2 bar plus 3 bar plus 3 bar, 6 bar, which is equal to what, 2 bar. So this is what the addition table. Similarly we can write a multiplication table. So here under multiplication, 0 bar, 1 bar, 2 bar, 3 bar, 0 bar, 1 bar, 2 bar, 3 bar. So 0 bar into 0 bar, 0 bar. Here 0 bar, 0 bar, 0 bar. Here again 0 bar, 1 bar, 2 bar, 3 bar. 2 bar into 0 bar is 0 bar. 2 bar, 2 bar into 2 bar, 4 bar, which is again 0 bar. 2 bar into 3, 6 bar. 6 bar is equal to 2 bar. 3 bar into 0 bar is 0 bar. 3 bar into 1 bar is 3 bar. 3 bar into 2 bar is 6 bar. and 6 bar congruent to what? 2 bar, and 3 bar into 3 bar 9 bar, which is congruent to what? 1 bar modulo 4. So this is the multiplication table for Z4. Now last example, example number 5. Example number 5. Prove that 6 divides n cube minus n for all non-negative integers. For all non-negative, that is positive integers, to integers. Now again we are going to apply here mathematical induction. Prove by using mathematical induction. Here step first, for n is equal to 1, the n cube minus n is equal to 1 cube minus 1 is equal to 0, and 6 divides 0, and therefore result is true for n is equal to 1. Step number 2, we assume that result hold for n is equal to k, where k is greater than or equal to 1. Result true for n is equal to k, that is implies, that is 6, we assume here 6 divides k cube minus k, that is this k cube minus k is multiple of 6, that is k cube minus k is equal to 6m for some integer m. From this we can write k cube is equal to 6m plus k. Okay, now in step number 3 we want to show that result is true for, prove that result is true for n is equal to k plus 1. That is, we want to show that 6 divides k plus 1 cube minus k plus 1. Now here consider k plus 1 cube minus k plus 1. As we know that a plus b bracket cube is a cube plus thrice a square b plus thrice ab square, that is 1 square is 1, so I am not writing 1, plus 1 b cube, that is 1, minus k minus 1. So here 1 will get cancelled here. The value of k cube from step number 2, step number 2 is 6m plus k. So if you replace here 6m plus k plus 3k square plus 3k minus k, so this plus k minus k will get cancelled here, and we can write this as 6m plus, from this two term we can take 3 times k outside, so inside the bracket k plus 1, as we know that k into k plus 1 are two successive integer which is always greater than what, greater than or equal to what, 2. So this number is what, this number is multiple of 6. Okay, these are the two successive consecutive integers, that is 2 3, then 4 6 4 5, okay, and so on. So here two consecutive integers, from this we can write this number, this is what, is 6m time plus 6k dash, as k plus 1 is equal to what, is always divisible by 2. This number is always divisible by 2. So from this we can write it is equal to 6 times k dash, and therefore if we take 6 outside, inside the bracket m plus k dash, and therefore 6, this number, that is k plus 1 cube minus k plus 1 is multiple of 6. This implies 6 divides k plus 1 cube minus k plus 1 and therefore this implies result true for n is equal to k plus 1, and hence by using mathematical induction we can say that mathematical induction we can say that 6 divides n cube minus n for every positive integer or non-negative integers. Okay, thank you.